In this video, we're going to be looking at action potentials within the heart. More specifically, we're going to be looking at those action potentials that occur in the contractile myocardial These are the ones along here that have those thick and thin myofilaments that when stimulated are going to contract. Now we saw previously that cells in the SA node or any of the autoarrhythmic cells can establish their own action potential. We talked about the pacemaker potential and then developing an action potential, and then it goes back and you get another one of these pacemaker potentials, then an action potential. That sets the pace of the heart. Well, each time we're going to see that you have this action potential happening, these cells, SA nodal cells, are in contact with the contractile myocardial sites. And they're going to stimulate those contractile myocardial sites to develop an action potential that looks like this right here. And that action potential is what's going to stimulate these contractile units to contract. And that's what we're going to look at in more detail in this video. So shown here is a sinoatrial node with cells that make up the SA node, and these cells are in contact with the contractile myocardial sites via these junctions right here. And what do we call those junctions? Those are the gap junctions. And previously discussed, we went over autoarrhythmic cells and how we have the movement of various ions through these voltage-gated channels in order to get the pacemaker potential and then the depolarization, repolarization of the action potential. And it just continues on, and that sets the pace of the heart. Well, each time you have one of these action potentials, we're going to see the movement of this sodium and calcium through these voltage-gated channels. Some of that sodium and calcium is going to go across this membrane right here that's attaching the autoarrhythmic cell to the contractile myocardial site. And some of that sodium and calcium comes in, and that's going to bring this contractile cell to threshold. When it hits threshold, we're going to see a depolarization. Then we're going to see this plateau phase, and then a repolarization. That's the action potential that happens along the muscle cell membrane of the contractile cell. Then when you get to the next contractile cell, some of those ions, sodium and calcium, are going to go across this gap junction and bring the next contractile cell to threshold and then stimulate that cell. Well, as these action potentials are traveling over these myocardial sites, we're going to see that that calcium coming in is actually going to stimulate calcium to be released from inside this cell, and it's going to cause those contractile units, those thick and thin myofilaments, to interact and give you a contraction. So the action potential isn't the contraction of the cardiac cell. The action potential is what tells the cardiac cell when to contract. So what we're going to do is we're going to focus on these cells right here, the SA nodal cells, and how they stimulate the contractile myocardial cells here. Here are those SA nodal cells. Recall, we learned that this sodium and calcium that comes in, some of that sodium and calcium is going to go across this junction right here. Remember what these were called? The gap junctions. The gap junctions are connecting these autoarrhythmic cells with the myocardial contractile cells. That's going to allow ions to go from the autoarrhythmic cell to the myocardial contractile cell. And these ions are going to move across, and what they're going to do is they're going to depolarize this myocardial contractile cell is at its resting membrane potential. It's going to bring it up to threshold to fire an action potential. And that action potential is going to go over the membrane here, this myocardial cell. And as it goes over the membrane, we're going to see that there's all kinds of ions. There's going to be sodium moving in. There's going to be potassium moving out. There's going to be calcium moving in. And these ions, especially that calcium coming in, is going to stimulate this myocardial cell to contract. We're also going to see that when you get to the end up against the next myocardial contractile cell where we have that intercalated disc, you also have these gap junctions. Ions are going to come through from one myocardial cell to the next myocardial cell and stimulate it to reach threshold to fire an action potential along its membrane so that it contracts. And this happens extremely rapidly. Remember, we're talking about that functional syncytium and those myocardial cells and the ventricles and the atria and how they contract as a single unit. These action potentials, as they travel over the membranes of the myocardial sites, that's what's going to give you these waves that are shown in an EKG. The P wave, the QRS, the T. These waves are formed by changes in voltages across millions of these contractile myocardial sites within the atria and the ventricles. And we're going to see exactly how this happens. Physiologically, it is extremely interesting. You thought autoarrhythmic cells were interesting. Wait till we get to the myocardial contractile cells. The action potential we're going to see in these looks like this right here. We're going to see sodium's going to come in, then potassium's going to leave as calcium's coming in during this plateau phase, and we have a repolarization with potassium leaving the cell, coming back to its resting membrane potential. So the action potentials that we see in the contractile myocardial cells look like this, whereas the action potentials that we saw in the autoarrhythmic cells look like this. So the production of myocardial action potentials, what happens? Well, as you can see here, we have the action potential that's generated along the myocardial cell membranes. It's labeled 0 through 4. So at 0, what's happening here? Well, action potentials from pacemaker cells are going to stimulate myocardial cells to go from their resting membrane potential of about minus 90 millivolts to depolarize to threshold, which is about minus 85 millivolts. That's the sodium and calcium that's coming in from this autoarrhythmic cell into this myocardial contractile cell. That sodium and calcium are positive charges. It's going to depolarize it to threshold. Once it does this, fast, voltage-gated sodium channels open and sodium moves into this myocardial cell. As it moves in, that's going to cause this depolarization to around positive 20 millivolts. At about positive 20 millivolts, these fast voltage-gated sodium channels close. Similar to what we saw with the skeletal muscle and the neural impulses. As soon as you hit that positive 20 or positive 30 millivolts, bam, voltage-gated sodium channels slam shut. That's exactly what's happening here in the contractile myocardial sites. Once they close, you have potassium leak channels that are always open, and potassium is leaking out. So that's going to cause a repolarization. You also have another type of channel, special channel called a slow voltage-gated potassium channel. That opens up to also allow potassium to leak through. What voltage does it open? At about positive 20 millivolts. Potassium is moving out, which causes this brief repolarization. And that potassium is going to continue to move out all the way down here to the resting membrane potential. So why then do we have this plateau phase? Why doesn't it just come right back down to this resting membrane potential with this potassium moving out? And the reason has to do with a very special type of channel. And that channel is called a voltage-gated L-type calcium channel. Because right here at the plateau phase, you see how we have calcium moving in? As that potassium is moving out, it's balanced by the calcium that's moving in. That allows for this plateau phase. So it's not just a quick repolarization as we saw in other types of cells. No, this is a plateau phase, and that calcium is going to move in as the potassium moves out, and this has a very important function in contractility of these myocardial sites. So at number 2, the plateau phase, make sure you know that this is a phase that we have voltage-gated L-type calcium channels open, which allows calcium to slowly enter the cell. Now this depolarization is maintained for 200 to 300 milliseconds before calcium channels close completely and then repolarization occurs. The plateau phase results from a slow inward diffusion of calcium through voltage-gated L-type calcium channels that's balanced by a slow outward movement of potassium through potassium leak channels, also through slow voltage-gated potassium channels. The resulting entry of extracellular calcium induces the release of sarcoplasmic reticular calcium stores, thereby activating the excitation-contraction coupling. Remember, we were looking at cardiac cells along the membrane of those contractile myocardial sites. As that action potential travels down this membrane, it's a movement of sodium and potassium in and out, it also opens up voltage-gated calcium channels. That calcium is moving in here. That's what we see here. The voltage-gated calcium channels are opening, calcium moves in as that potassium is moving out. Well, that calcium that's coming in is giving you that plateau phase. The calcium that comes in, remember, is inducing the calcium to be released from the sarcoplasmic reticulum of those myocardial sites. Calcium binds onto these calcium release channels. It opens them up so that calcium will leave out of the sarcoplasmic reticulum. And then this calcium, along with the calcium that comes from the outside of the cell, is going to participate in binding onto troponin C, moving the troponin-troponin complex out of the way so that the myosin heads within this contractile cell can bind onto the actin filaments and slide them over each other, causing contraction of the cell. Now this happens for 200 to 300 milliseconds. That's going to give a long contraction of these myocardial sites. So for example, when we're looking here, we're going to see in a little bit, that plateau phase that we have here allows for these myocardial sites to contract for a longer period of time before they relax. That longer period of time is going to provide enough of the contraction to move the blood. If it was just a single contract, relax, you're not going to be able to pump very much blood through that heart before it relaxes. But you have this long drawn out contraction, these myocardiocytes, which gives time to pump the blood through the heart. And we'll go through the significance of this in a little bit. Just want to get you an idea on the beauty of this plateau phase, which allows that heart to contract for a longer period of time, those myocardial contractile cells. In phase 3, you have this rapid repolarization at the end of the plateau phase. And this is achieved by the closing of voltage-gated calcium channels and the opening of rapid voltage-gated potassium channels. In addition to the slow voltage-gated potassium channels that are also open, this is going to cause that repolarization. And you'll come back to the resting membrane potential. At number 4, this is the resting potential. Those rapid and slow voltage-gated potassium channels close, and the permeabilities for sodium, potassium, and calcium return to the resting levels. Ion pumps are going to actively pump calcium into the sarcoplasmic reticulum and out of the cell, along with the sodium-potassium pumps. That's this right here. Remember, you have those calcium ATPase pumps. They're going to pump that calcium back into the sarcoplasmic reticulum. You also have calcium pumps we're going to see. They're going to pump calcium out of these myocardiocytes, out of the cell, keep the level of calcium higher outside the cell. You have sodium-potassium pumps. They're going to reestablish the sodium-potassium gradients. Interestingly, I'm talking about these slow voltage-gated potassium channels. We have the potassium leak channels. There's a lot of different potassium channels. In fact, if you really wanted to get into it, you can go into the electrophysiology and you're going to see that this plateau phase, for example, right here, has a number of different channels to allow this to happen. We've gone through a few of them, which is fine. For what you're going into clinically, this is where you need to be, understanding this. But realize that if you really want to go into more detail on this, that there are a lot of channels that are involved within these myocardial sites. If you have any questions on this, do not hesitate to ask. Real important to understand all of these different channels, because when we're talking about the pharmacology on how you treat disorders of the heart, including hypertension or various types of arrhythmias, the drugs that are used to treat these arrhythmias are targeting these channels that are either on autoarrhythmic cells or myocardial contractile cells. It's a really, really interesting area. So what's the significance of this plateau phase? Well, that prolonged plateau phase functions to 1, it's going to increase cardiac contractile time to ensure adequate time and strength to eject the blood. This is extremely important. When we were looking at skeletal muscles, remember how we talked about the twitch, which is a single contraction, relaxation? On a twitch, you have depolarization and then rapid repolarization. So it depolarizes and then it'll repolarize. If that happened with the contractile cells, they would contract very quick and then relax. We don't see that, though, with contractile cells, because that wouldn't move the blood through the heart. You need to contract for a longer period of time and then relax in order to have the movement of blood. Twitch wouldn't do that, as shown here. It just wouldn't have a long enough contraction. So having this plateau phase where this calcium is coming in is going to cause these contractile cells to contract for a longer period of time. That's going to allow time for blood to move from the atria into the ventricles. And then the ventricles are going to pump out that blood. Because remember, during that time, that calcium is coming in from the extracellular fluid in that plateau phase and stimulating calcium to be released from the sarcoplasmic reticulum. All of that calcium is interacting with that troponin C to move the troponin-tropomyosin complex out of the way so that the myosin heads can bind and power stroke. In what period is this calcium interacting with these contractile proteins to get the contraction? That's during this plateau phase. So you absolutely have to have the plateau phase in order to increase cardiac contractile time. It also provides a long refractory period, and this acts as a protective mechanism in the heart by preventing multiple action potentials from occurring. It limits the frequency of depolarization and therefore the heart rate. This is important because at very high heart rates, the heart would be unable to adequately fill with blood, and therefore ventricular ejection would be reduced. So it gives you that filling time. It gives you that relaxing time to fill with blood.